Thank you for joining me here. I have a long list of very informative questions from our audience. Thank you everyone who submitted the questions. I will do my very best to cover as many questions as I can. The first question I see here looks like this is for you, Jithin. Do you use the same hardware and software for both HPC and AI workloads? And do the workload optimizations differently for this?
Sure. Yeah. Thank you. I think this is a great question. So we have different VM types for HPC and AI workloads. So we call it as the H series and the ND series. So like, for example, like if an MPI or scientific code doesn't really need GPUs, right? I mean, you can like a lot of high memory bandwidth CPU cores and also at the same time high bandwidth interconnect, right? So that's H series. But at the same time, like if the HPC code wants to take advantage of GPUs, yeah, there is a ND series. But again, like you mentioned, the workload optimization is completely different in those two scenarios. So yeah, so we support.
So in summary, you do look at what is the workload you want to run,
yeah,
and optimize the stack across.
Exactly. Okay. Yeah.
Cool. Weiwei, I think this question is for you. What is the nature of tensor parallel communication in Llama training? What are the typical flow sizes in bytes? Is TP throughput bound or sensitive to NVLink latency? And what latencies are acceptable for GenAI training?
Yes, thanks. This is also a great question, and it's bothering us a lot in Llama training. So the nature of tensor parallelism, it is the communication of intermediate activations. The normal communication data size will be a few hundred megabytes each. So it will saturate the network bandwidth. So it is more sensitive to the network bandwidth than latency. And what is the last question?
So what latencies are acceptable?
Oh, okay. So the usual latency for tensor parallelism is within a few milliseconds.
Okay. So in summary, you're saying it is throughput bound, not as much
Yep.
sensitive to latency. Thank you. Arnab, looks like this question is for you. How can we statically assign ranks to ML workers to be topologically started? Don't we need runtime state, actual traffic stats across all NIC pairs?
Yeah, this is a really good question. So what we actually do at Meta with MAST is MAST will topologically sort the hosts and pass them to the training application. When the training application starts up at application initialization time, the training application will use this topologically sorted list of hosts along with, when it's doing the initialization, it'll figure out, okay, which groups are doing TP, which groups are doing PP, which groups are doing data parallel, and then it'll perform rank assignment. So it's not quite runtime. I would say this is more like an initialization thing. Mm-hmm. So when the training application starts up, that's when the actual rank assignment happens.
Okay. And if I were to interpret this question a bit more, any runtime state, is there a need to go and reassign the ranks or?
Not that I'm aware of. Usually it happens once at init.
Okay.
And then the ranks are there, for the lifetime of the application. Yeah.
Okay. Thank you. Adi, looks like this question is for you.
Yeah.
Can you expand why traffic engineering did not operationally scale beyond two-layer claw network?
Yeah. So I think I touched upon traffic engineering in terms of like scalability issues. Naturally, when you have more network hops and larger jobs, the complexity of the calculation takes much longer. And that means that you may not actually have that calculation ready within your job initialization time and things like that. That means that you don't have a load balancing solution interim in that duration. So that was one reason. But overall, I think the biggest reason is more around operational complexity. At Meta, we give a lot of importance to operational complexity. If something's a great solution, but nevertheless it comes with a breakage every week or something like that, or something that we need a lot of software engineers or engineers to actually maintain, then we discourage that solution naturally because we want to move more fluidly and stably. So in general, a three-layer claw presents us with multiple vendors of switches, and to actually develop the traffic engineering solution in order to assign specific kinds of demands with different vendor switches, managing all that complexity, managing bugs in their own switch OS and things like that was overall operationally very, very unscalable. One funny thing that I'd like to add, around here is that we did not move from traffic engineering scalability issues to ECMP like right off the bat. We actually tried to see if we can continue to use traffic engineering for the first 2 network hops, but then for the traffic that crosses the AI zones, maybe we can use ECMP. But then even that was actually ran into problems because traffic engineering would make its own determinations in terms of like sometimes it would take 8 links worth of traffic or in a rack and assign it to 8 links. And ECMP, that was meant to balance the traffic across the AI zones, that would allocate traffic to all 16 links. And so 8 of the links will be overloaded. So there's a lot of operational issues overall in terms of that prevented us from not using traffic engineering for Llama 3 training.
So as a summary, you would say operational complexity, reason 1, and the amount of effort to make it scale to larger networks as reason 2.
That's it.
Okay, thank you. We have a network topology related question. I think Jithin, maybe you can take this. When we design and deploy AI networks, we aim to keep the network very symmetric. Mm-hmm. How important is to keep the running state of the network also symmetric?
Sure. Yeah. So to be honest, it's very hard to keep symmetric all the time, right? Mm-hmm. But at certain layers of networks, it makes sense, right? So to keep a very close eye on those links, and then how symmetric it is, right? Sometimes, like otherwise, you are relying on the smart switch or other network or switch-related congestion protocols to take advantage, right? But if we can handle these symmetries in a close monitoring, then it's actually much better for the runtime of this training job. So in our case, at the lower layers, we don't really care. But especially at the top layer where we have really high oversubscription, we keep a very close eye and then rely on these manual strategies. Yeah.
That is very insightful, Jithin. So lower layers of the fabric, not a big deal. Mm-hmm. Higher layers of the fabric, do your best to keep the runtime state as symmetric as possible. Thank you. We have a scheduling question, maybe Arnab. This might be for you. The talk was focused on impact of scheduling and sharding on network efficiency. In addition to these, are there other objectives that you have tried to optimize? Or also, are these objectives in conflict with each other?
Yeah, so this is it's a good question. So basically, I had highlighted a couple of other things, so like scheduling overhead and fault tolerance. But in addition to these, we have even more constraints for job scheduling for ML training. So I'll call out a couple of the big ones. One of the big ones is data locality constraints. Mm-hmm. So for example, if your job needs a particular training data set, and this happens to be the case more for non-Gen AI workloads, such as recommendation system models workloads, then they have a Hive dependency. But these data sets are not necessarily located in every single region.
Okay.
So training data and compute co-location it's a huge focus area. Mm-hmm. And specifically per job, we will have data locality constraints. And then we will have to identify the set of regions that the job can be placed in. So that's one very large set of constraints that we have to work with. Another big class of constraints is GPU quotas. So even though we have at this point hundreds of thousands of GPUs, we have many different orgs and teams within those orgs that need to use these GPUs. So what tends to happen is you get logical quota assigned to you. The physical resources are not assigned to you because demand tends to wax and wane, right? So at runtime, we basically need to look at the real-time quota utilization per product group, okay, and then issue preemptions. So this is a huge focus area for us as well. Okay. So data locality constraints, quota utilization with respect to statically granted quotas, and then the network affinity constraints along with scheduling overhead and fault tolerance. So there's a lot of competing constraints, and at times we have to relax some of these constraints, or incur scheduling delay or excessive preemption. So it's a pretty hard place, but this is an active area of optimization that we're working on.
Is there an order of preference between these constraints that you use?
Well, it depends on whether they're hard constraints or soft constraints. So network affinity constraints in general, at least for like Llama, what we're observing, we initially thought they may be soft constraints, but they're not. They're hard constraints. So network affinity, I'd say it's a hard constraint. The quota one, we've tried to kind of make it layered. So if your product group is over quota or under quota, and then if your tenant, so within PGs, you can have teams. So if your tenant is under quota or over quota, right?
Okay.
So then there's a layering where it is more of a soft constraint, but at some point it becomes a hard constraint if the PG itself goes over quota. And then for data locality, that is a hard constraint because we do not want cross-region reads, right? So this doesn't apply to GenAI models. It applies more to Rexus models. But the volume of data being read means that, hey, if we allow these applications to read cross-region, we're going to melt the network, right? So that is a hard constraint.
Sure. So in summary, the prioritization is not a total ordering, but there are two buckets,
right,
whether it's a hard constraint or a soft constraint.
That's right.
Okay, makes sense. Thank you. This question, I think it's for you, Pavan. If the inference decode parallelization is network sensitive, and you ended up using direct data access for it, is it possible to apply this for scale-out communication during training? And are there any constraints that are preventing us from applying it?
Yeah, it's a good question. Hard question. Let me see what I can answer. Inference and training have very different properties in some sense. Training, for example, if you look at the lowest, innermost level of parallelism in training, tensor parallelism, the bigger bang for the buck we get is not in shaving latency, but trying to overlap it with computation and communication. That's where we get a bigger bang for the buck. So that's where we want to try to optimize it. Inference, on the other hand, goes through a lot of pruning, quantization, and so on to try to simplify the models already. So there's not much opportunity to do overlap of computation and communication, which makes it extremely latency sensitive. So it is a problem for inference, but the problems need not be exactly the same between training and inference. One thing I could potentially add is for inference systems, it is very latency sensitive. I think someone asked a question to Weiwei saying that what is the acceptable latency? It's a different answer for training and inference. Obviously, for training, it's fine if you can overlap it. For inference, the only real acceptable latency is 0. So that's whatever, however close we can get to that. It's essentially a product perception thing. So the closer we get to 0, the better the product will appear to the user.
Okay, so the main takeaway is in training, you have the opportunity of hiding your network latency behind compute. So you need not really optimize it as much as you have to do for inference workloads. Yeah. Thank you, Pavan. Okay, we have another efficiency question, but in a different angle. Weiwei, maybe you can take this. Your talk mentions about 40% GPU efficiency during training. What are some potential opportunities to improve this further?
Yeah, this is the thing that I have been working on every day. I can think of a few ways. First is to change the parallelism combinations. For example, in Llama 2 training, we only use the fully sharded data parallel and the tensor parallel, which we call the combination is 2D parallelisms. But for Llama 3 training, we use 4D parallelism, which is a combination of four parallelisms. This gives us good speed up at large scale and for larger models. The second way to do this is to do communication and computation overlapping. For example, in my talk, I mentioned that in the communication of TP is blocking because the outputs of the previous computation will be needed for the next computation. One way to mitigate this issue is that where we do the matrix multiplication, we do them part by part. After we finish a small part, we do the communication for this small part. Then we can achieve some kind of overlapping between the communication and the computation. And the third way to do this is to do model co-design. For example, in Llama 3, the full 5B model has only 126 layers. It was reduced from 128 layers. So only by reducing 2 layers, we are able to fit the GPU, fit the model more balanced in GPUs. And this also gives us a speed up.
Thank you.
Yeah. Shashi, if I may add.
Yeah, please.
Actually, it's a pretty fascinating question. It's a question that all of us are trying to answer, right? Overall, I think it's quite fascinating to think of training as a large parallel problem with a large amount of resources that you have at your disposal. And you want to map this like parallel mathematical problem to the amount of resources, right? So how you improve your efficiency is basically try and think of all the ways you can do this mathematical work on all of these, hardware resources you have, and try and find like if possible, a global minimum in terms of like the fastest you can do it, right? That means that, you can divide the work in many, many ways, and there are many ways in which you can do parallelizations, right? Like we talked about, there are 4 dimensions of parallelism, but in terms of how you can adjust how large is each parallelism direction, right? Or how you implement each parallelism. So, those I think Weiwei already touched on, where we talked about how we schedule and how we kind of place, and there are many, many combinations as Arnab touched upon in terms of how you place that, right? So, and apart from that, now, after you place them, there is some of the placements are much better suited for a particular network topology and load balancing and a bunch of other combinations, right? There are more combinations in terms of you take each parallelism and then it produces a particular collective like all-gather, and all-gather can be implemented as ring, tree, or so, right? So there's so many different problems in terms of and layers of software and hardware that you can optimize things for. And improving efficiency comes actually, it's a very multidisciplinary problem, if you will. And each layer contributes to some efficiency, right? Yeah.
So in summary, we need not settle for 40% utilization. There are opportunities across the training stack to improve this up. Cool, thank you. I see actually 2 questions here with the similar theme. And these questions are from your talk, Jithin. I'll pick just one of them.
Sure.
And you refer to NIC-based routing to enable better load balancing and congestion control. Can you share your perspective on pros and cons of implementing this on the NIC versus in the fabric?
Sure. And yeah, please don't get me wrong, right? Both has its own plus also, right? Plus and minuses also, right? So why we are looking more towards the NIC-based schemes is that maybe you can get faster response times, right? The problem is localized. You may be able to detect and react faster. But the RTTs are going to be different in case of switch, right? But again, that being said, we are yet to see how this is in action in a really large scale. So yeah, we are moving towards that, assuming this will be much faster and more efficient. But yeah, we still need to try this in production and get a live feedback. But yeah.
Okay. Would there be a consideration for one versus other based on the operational simplicity of the solution?
Actually, the operational simplicity may be smaller for the NIC base because everything is local.
Okay.
And you can also, the beauty is that you can actually get these hints from the CCL, right, and pass it in. Okay. So application of the user will have much more fine-grained control there, right? So and even decide which schemes we can pick or which routes we can pick, right? So that way it may be more elegant than relying on maybe some standard-defined set of protocols.
Okay. So in summary, you would like to wait until you learn the lessons from production.
Yeah, yeah.
But there is a sense that a NIC-based solution might be simpler.
Correct, yeah.
From an operational point of view.
Yep.
Cool. Adi, this question is for you. It's coming from your talk. In your presentation on collectives deep dive, you mentioned the data is copied twice inside the host, from compute buffer to channel buffer and from channel buffer to NIC. Is it possible to optimize this further?
Yeah, that's an interesting point. Yes, absolutely, it's possible to optimize it further, especially for certain collectives that don't have mathematical operations in them. You don't potentially need to implement 2 stages of copy because there's, you can directly write from source buffer to the destination buffer. However, that comes with quite a lot of challenges. It requires changes to the collective communications library architecture, as well as PyTorch or the ML framework or the application that registers this memory as well. So we actually did some work in this direction. We implemented user buffer registration or zero copy in our internal communications library. Then we worked with the NVIDIA Nickel team to actually open source parts of that and collaborated with them. And I think in the latest Nickel version, if you want to check out like user buffer registration or zero copy or direct copy, for certain collectives or certain collective operations like send receives, it's supported where you can directly write data from the source compute buffer to destination compute buffer. Obviously, it's new and it's still being like tested, and it has other implications to overall network in terms of you now being flooding the network too much or so. But nevertheless, I think definitely I think it's available to try it and check it out. And we are also looking deeper into it in terms of how to optimize this direct copy implementation for our future models and future applications.
I have a follow-up question, Adi.
Yeah.
So you said you have implemented this for a subset of collectives.
Right.
Is that because you want to experiment there, or the limitations that this wouldn't make sense for other collectives?
I think I'll answer a little bit, and then maybe Pavan, you can add. There are essentially it's easier essentially to implement for pure copy-based collectives where you just have data movement, right? So if you just have data movement, then the interim buffer is not as critical because you don't need to copy this data to an interim location, do some math or do some operations on top of it, and then send it out on the network, right? So for copy-based collectives is much more straightforward, and that's where I think we've implemented, as well as I think the NVIDIA Nickel team is I think opened up support for it. For mathematical operations also, I think it's possible to save copies, but it takes more work because there's more handshakes involved. Pavan?
Yeah, I think Adi covered most of it. It is, in theory, possible for all non-reduction collectives. Reduction collectives, if you have direct load store access, you can load it directly into a register or NVLink, for example, from the remote process. So that is, you can think of it as a zero copy because you're loading from memory directly into a register. But there are some collectives, like internode reduction, for example. I don't know how to do zero copy for internode reduction.
So any collective that doesn't involve the reduction operation, we can apply it. You're fairly early stage in terms of journey of going this direction. And not just Meta, entire community needs to learn and share lessons. Thank you. I have a question on context parallelism. Maybe Weiwei, you can help us here. Can you please explain when context parallelism would be used and how performance of models which will be using this might be limited by what the network can or cannot provide?
Yeah, thanks. Context parallelism is a new parallelism we introduced in Llama 3. It is especially used for the long context training phase. So if we have long context, I mean that we will try to calculate the interactions between a large number of words or tokens. So it will be, so the long context, one context will include several documents. So context parallelism will suffer from the different lengths of documents. What can make it worse is if we put context parallelism, the GPUs across AI zones or anything, it will introduce more imbalance in the context parallelism part, the communication, which will introduce way more imbalance across multiple data parallel groups, and it will greatly slow down the whole training.
Okay.
So it is very important for context parallelism to utilize just the cross-rack internet.
So summary, pack them as close as possible from a network point of view. Don't spray them across longer network distances. Okay, Thank you. Uh, the next question is very interesting. I don't think it is targeted at any particular talk. I will let multiple of you to chime in. Can we imagine a future where ML scheduler can automatically perceive the job sharding and make the most suitable scheduling decisions? Do we see any impediments in going towards that reality? Maybe Arnab, you can start and others could chime in.
So I think if we're talking about the types of job shards, model sharding that Weiwei was talking about, so at least at Meta, we're trying to be agnostic of the various parallelism techniques because AI is very rapidly evolving. I mean, every other day there's a new parallelism technique, right? So by encapsulating these parallelism techniques as primitives in the scheduler, the risk that we would run is that they would quickly become obsolete, right?
Okay.
So what the approach that we're taking is, if you can have an abstraction layer in the scheduler where topological constraints can be expressed, then higher levels in the stack, which are decoupled from the scheduler, can then evolve more rapidly to deal with new parallelism techniques, right? But sharding can mean multiple things, right?
Sure.
Now, if you're talking about, hey, can we run an ML model? 2 years back, we didn't have the ability for ML models to span AI zones. The largest ML models, I think, even a year and a half ago, were I think less than 1,000 GPUs, right? And there's more than 3K GPUs in an AI zone, so much smaller than what an AI zone can accommodate. With Gen AI, it's been exponential in terms of model growth, right? So we've had to very rapidly figure out how to kind of build very large-scale training clusters and have very large job sizes, right? So that is a different type of sharding, if you will.
Okay.
And for that, yes, I think we have to keep evolving the scheduling system so that all of the internals of the scheduling system, there's a lot of distributed systems challenges that we have when scaling beyond a certain size. So that I feel like is an evolving problem, and I think we'll continue to kind of hit new scaling limits there. Yeah.
Okay, so your opinion is rather than the leaking the abstractions of how you are sharding and scaling your model to the scheduler, encode them in primitives that can be hold true for various techniques, and scheduler only will deal with those semantics.
Yeah.
Okay. Pavan, Adi, you want to chime in on this question?
I can perhaps add a few things. I think it's a good goal to have. I feel it's a little, right now it's a North Star, right? That's what I want to get to. Most times when you're doing these large scale training systems, we are at the cutting edge, right? We are building the largest clusters. We're building not Meta, Microsoft, Amazon, all of these companies are building the cutting edge clusters, which means there's not enough training data of what to do when something goes wrong, because we are learning what's going wrong for the first time. So in order to have an ML scheduler that does automatically figure out what's the best thing to do, we as humans need to know that first so that we can train it. Unfortunately, we are not there yet. We are figuring it out on the fly. I don't know if you guys have seen that video of this train is running on a track and there's a duck sitting in the front and laying the tracks while the train is running. That's what we're doing.
But if someone can...
I like the analogy, Pavan, and can relate to that. Yes, Adi.
Yeah, but if someone can solve this problem, I think there's multiple startup ideas out here. It's a hard problem to solve, I think, overall. It's mainly because I think, like Pavan talked about, there are different parallelisms. And now I think the model that we're using is that some expert model developer or infra person look at all of these parallelisms and understand, what is the inner layer of parallelism, outer layer of parallelism, what is very network sensitive, what is not network sensitive. And then based on that, they will give those constraints up to the scheduler. Now, for a piece of software to actually perceive the sizes of the messages that are going, the network topology, we're looking at a controller of controllers, if you will, that can potentially do this. And it's typically a very, very hard problem to build that and actually make it scale in production. But it's an exciting problem, or it's an exciting problem. Definitely, I think if one of you can solve it, I think it means a lot of money, basically. Yeah.
I have many more questions here, but I will pick one last question in interest of time. And Jithin, you talked about Superbench. If say I'm a vendor or working for a vendor, how can I leverage this to test my product before I send it to customers?
Yeah, Superbench is actually expandable. So all it takes is a YAML file where you describe your system. So yeah, I mean, like there are YAML files for the different the machine types that we use. But yeah, it can easily be abstracted it out to any of the new different upcoming node types. So yeah, and it's all open source also. So yeah.
So we can extend it and customize it to the product that I might be building.
Absolutely.
Cool. So we are at the end of this session. Thank you for patiently answering these questions. Thank you for sending the questions in. Unfortunately, I couldn't cover everything, but still, we can probably continue the conversation after we've wrapped this up. Now I would like to invite Rajiv to come here and help, wrap today's conference. Thank you, folks.